So we have Jason Moore here today, starting out the afternoon session. He'll be presenting on SymPy for solid body, for rigid body dynamics. And Jason comes to us from UC Davis. So thank you very much, Jason.
Welcome. Thanks for coming to my talk. Like you said, I'm from UC Davis. I'm a mechanical engineer and more specifically a dynamicist and control engineer. And we work a lot with modeling sort of the macro world with rigid body mechanics. And I'm going to talk about some software we've developed, in particular in SymPy, to come up with equations of motion for rigid body systems. Just to remind ourselves what rigid body dynamics are, it's the study of the movement of systems of interconnected rigid bodies under the action of external forces. Most of you have probably experienced this in your physics courses, right? A mass on a spring or various other throwing a baseball and seeing where it lands and figuring out the path. These are classic physics problems, and they're described by these two important equations of motion called the Newton-Euler equations. On the left, the first one says that the sum of the forces has to equal the change in linear momentum. And the second one is that the sum of the torques acting on the body has to equal the change in the angular momentum. And these two important equations, turns out that they govern a lot of the motion in our world at the macro level, from planetary systems to me standing here walking. But these equations in high school, college physics, they're very trivial. But as you try to add more bodies to a system, things get really nasty. The kinematics are highly nonlinear, and these equations start to grow in great length. In particular, I've been working with just a 4-body system for much of my graduate work, and at 11-point font, it takes up like 30 pages of 8.5 by 11 to just see these equations of motion. So things get nasty quick, and so we turn to computational methods to handle that, right? You can no longer write those by hand. And what's it good for? Just specifically, from robotics to spacecraft dynamics, from planetary motion and vehicle dynamics, almost anything that's moving at the macro level, and you want to understand how it moves, you use these equations of motion and methods to find out how they move. So there is a lot of software that exists. They're typically classified in what you'd call maybe a physics engine. I've listed a few types, a few that you may know here to the right. And there's two fundamental types. One is the kind that runs video games and such, that are usually for real-time, fast computations, but they're very low fidelity. They may be making lots of approximations on the motion of objects. They just need to look right. And then the second type is the high fidelity, high precision. And that's the type that we're concerned with more with this project. We want to get the correct equations of motion and be able to very accurately model and simulate rigid body dynamic systems. And another thing to note too is the closed source systems that I've been familiar with and that sort of drove us into writing our own, they don't really allow you to do reproducible work. When you have these complex equations of motion and you want to know if researcher 1 and researcher 2 are using the same model, if you have closed code, we can no longer just look at a piece of paper where a small derivation was and compare that we have the right equations of motion. So we need to be able to share code. And these closed source packages, some of them are unbelievably, the really good ones are like $20,000 a seat. So we're trying to come up with a competitor that fundamentally can allow us to do this kind of workflow and not have these unbelievable price points, and also have more flexibility in the reproducibility aspect. So our goal is to create a project that is competitive with these kind of packages that we traditionally learn in engineering, but we're going to take open source to heart and create something that's better in a lot of ways. And we have a couple of parts here. The main overarching part we're calling PyDy, and you can visit pydi.org to see some details of what that project's going to encompass, but it's going to really encompass the whole picture from modeling to simulation and visualization. But our core is based in SymPy. And we've developed a package there called SymPy Mechanics. It's in the physics, under the physics subpackage. And its fundamental purpose is to derive equations of motion for these systems symbolically. And then the question is, well, why symbolic? Many of the packages that I showed you up there, they're numerical packages. You start at the beginning of your problem and you develop, you find your equations of motion and such, and go to simulation, et cetera, all in numeric domain. But the symbolic gives you a lot of interesting ability. It maps well to hand derivations, and you can, for small problems, you can visually inspect and compare problems. But you can also generate faster numerical code if you properly build up your symbolics. And it makes it easier to take your code and straight to paper when you do want to actually print things out. And the software that we've developed in the mechanics package, the main features are that we can basically deal with rigid body dynamics, as many bodies as you want. Now, we haven't tested thousands and thousands of bodies, but if you have enough memory, we're hoping that you can do big multi-body problems. And it allows you to do very easy definition and management of the kinematics of a problem. Once you get into the multi-body problems, the kinematics are the tricky part. That's the fundamental hard part, and adds the complexity. And getting the kinematics correct is where you really want to focus and make that easy to do and less error prone. And the other things, we can handle non-holonomic and holonomic constraints, right? So like rolling without slip and different motion constraints. All that's handled. We also have automatic equation of motion generation. So once you set up the kinematics, we have methods in there that automatically go from the kinematics to the equations of motion. And finally, we have automatic linearization of systems. So a lot of times, particularly for control design, you deal with linear systems. And so we can automatically symbolically linearize the equations of motion that we develop with this package. It's made up of a few submodules here. I'll just briefly go through them. The first one, Essential, basically takes care of the basics of vector calculus, but it extends that and takes care of managing all your vector calculus when you have, you can have 100 different reference frames where you define different vectors, and you can still compute all the vector calculus that you need to and keep track while you're through these sort of tree of reference frames. So it manages the vectors and reference frames. And the functions, we have just a lot of convenience functions like getting angular momentum from a system or energy, or a lot of our methods are pushed up at sort of a high level, so you can just call dot instead of having to drag that out of a method to do a dot product on a vector. And then we have the next three, point, particle, and rigid body, start to handle. Points help you track the location of points in space and their velocities and accelerations. And then particle and rigid body are the two concepts. Those are the fundamental pieces in rigid body dynamics. A particle has a mass and a point, and a rigid body has a mass, a center of mass, and a reference frame attached to it, and it can rotate. So those track that information. And finally, we have these two modules that sort of implement the automatic equation of motion generation from the kinematics that you provide. So I'm going to jump into sort of three demos to give you an idea of how the software works. So the first one, and all these are online. I'll jump back to that slide and you can see the results. But fundamentally, we start off. We can import. I import symbols from SymPy, and I bring in everything from the mechanics module, and brings in a lot of top-level things, including reference frames and points and particles, and a lot of these elements that I just talked about, vectors. And the first thing that you typically do is you want to build up vectors to work with. So a reference frame is defined by the simple command, and then we have and it creates an object here, and the main pieces is X, Y, and Z are the unit vectors associated, the orthonormal unit vectors associated with that reference frame. And we can use those unit vectors then to build arbitrary vectors. So here I've built a vector V that's 1 unit in the X direction of the N frame, 2 in the Y, and 3 in the Z. So this is a vector, and we can take a look at it. We can do all kinds of operations like multiply and divide. You can add vectors, subtract vectors, and then we have some other methods that are useful, like getting the magnitude of a vector, normalizing it, right? So you can get a unit vector in the same direction, and you can do dot products and cross products, right? So we have sort of all the basic vector calculus elements that you want, but we're also in mechanics. I mean, we're also in SymPy, so we can do everything symbolically. So I can define vectors with constants instead of numbers, and all the same methods work, and they're going to give you all the vector calculus that you need to start building up systems. Another key thing, when you have multiple reference frames and you start to talk about motion, when we differentiate vectors, we always have to know which frame we're differentiating with respect to. So the diff method off of any vector, you give it a frame and the item that you want to differentiate with respect to, and it handles that seamlessly. So we can also introduce a second reference frame and orient it relative to the first. And we see that the new reference frame, if we ask for the direction cosine matrix relative to the in frame, we now have that tracked. And so we'll build up trees of you can rotate reference frames with respect to each other, and you build up these trees of direction cosine matrices to manage how all these are interrelated. And then you can start expressing vectors in different reference frames. So in the first, let's say, take that v vector we originally expressed in the in frame and show it in the in frame. So you get the picture there. I got 5 minutes left. I'm going to jump to the second one. This is a classic problem, mass spring damper. Very simple. We know the equations of motion to the mass spring damper. It's mx double dot plus cx dot plus kx equals the gravitational force that's acting on the damper. And we can use this software package to develop the equations of motion. And being that, if I got a little more time, I think. So the new things here to notice are that I introduce a reference frame for the ceiling, some points to track the origin and also the point that's mapping the mass. And I can set velocities of the point, and the origin has no velocity, and then I give the velocity of the point, the two variables that I assigned here, x and v. And finally, I can sum up the forces on the object, and I have a force vector in the x direction, the down direction, that gives me all the forces acting on that particle. And then just to solve Newton's equation, F equals ma, I can use SymPy just to manually set up that equation, and then I end up with the equation of motion right there. And it's a second order differential equation, ordinary differential equation. And I can solve and put it into first order form, which most numerical solvers typically take. And then, but finally, if I want to, this can also be automated, like I said, with the Kane's method or the Lagrange's method. And I can just pass in the generalized coordinate, generalized speed, and the kinematic differential equations, and it also will give me that same result in first order form there at the bottom. So this is a very trivial example that you can just write by hand, but when you start to get complex systems like this next one, we need the help of the computer. So here I have a pendulum on a cart, except that I can have n number of pendulums on top of each other, and I can slide the cart back and forth freely too, and apply a force to the bottom of it. So I'll quickly go through this code. We do the same thing. We introduce the various dynamic symbols and the constants. We set up points and to map where all the masses are and the links. and generalized coordinates to map the angles of the thing. And in this loop here, we go through, depending on, I've got n equals 5 at the top, but depending on how many that you add, you know, it'll generate all the forces and the particles and everything that's needed to construct the equations of motion of that system. And then I call my automated method the Kane's method here, and I give it the results that come out of that loop, and it gives me the equations of motion. And this spits it out in Kane's form. And you can see that many bodies starts to make problems more and more complicated. So that was 5 links. So you can see why it's useful. Writing that by hand is a nightmare. The next bit here, how many minutes? Just one? Oh, it was until 2:30? Oh, I get 5. I got it. I'm cussing on the video too. Well, let me just show you this one video to end it down here.
Question. Can you show us the video?
Yes, I'll show you the video. So the rest of the bit here is the simulation. And so I'm making use of matplotlib, if I can find it. Right, and once you get the equations of motion, then you can see how it behaves. All right, and so that's what a pendulum of that would do. Yeah, so it dances. The bit, you can check out these notebooks, and at the bottom here, I've added a controller, right, and then you can balance it. So you have these equations of motion now give you the power to simulate these systems. And Andrei Sertic, he asked me after I showed this to him the first time whether or not that could really happen. And this is a robot, not one that I have been involved with, but and they actually swing up a 3-to-3 pendulum and balance it, the robot. So they're using these equations of motion that, you know, are generated from this kind of systems to do this kind of work. And just to end this real quickly, there's some future stuff. We've got some cool GSOC projects. We're going to add electromagnetics, so you can have magnetic fields, and we're going to have 3-dimensional visualizations in the browser. I didn't do all the work on this. I did very little. These are the guys that did all the grunt work to make this stuff kind of happen. And that's all. Thank you for your time.
So we have time for a couple questions. Hi. I noticed you imported the control systems library for Python at the index of the controller design.
Correct.
Do you know the trajectory of that project, where it's going, what the chances of interacting more with SymPy are? Because when I use it, I find it could benefit from interacting more with SymPy than it currently does. And if you want to put that under your umbrella.
Yeah, I have long-term goals of trying to help that project grow more. Oh, sorry. He's asking about the control library. There's a Python control library that's trying to mimic a lot of the functionality that you get in MATLAB. MATLAB is sort of the king of control design, and we don't really have a good alternative in the open source world. But I know Richard Murray at Caltech is sort of the guy behind that, and I watched the mailing list. It's sort of a slow, they're not a real active project, but people are contributing here and there, and I've seen some professors using some things. So I think if you just put it on GitHub, you know, and get off SourceForge, that it can make a big difference too. But so I think it has life, but slow.
Any other questions?
I know Lagrange equation of motion. This Kane guy, is that a recent thing? Or?
Yeah, it's relatively recent. So Kane was a professor in Stanford. He is about 85 years old right now, and he wrote a book called Theory of Dynamics and Applications. And he came up with this method called Kane's method, and it's sort of controversial in the name, whether it's a new thing or not, but it lends itself very much to computations, and he's very thorough about all the details of the kinematics and managing all this, and all of the good software packages that do this kind of stuff, they use his method. Most of them do. Oh, yeah. It's performance? Yeah. right now we've got some nasty problems. These like I can put n equals 50 on that to try to get a link, and SymPy hogs all the memory in my machine and basically crashes. And so there's some limits in terms of certainly memory, but also speed of computation with SymPy. If you saw how those equations were just this simple 5-body problem, but if you have motion constraints and lots of other things, generating that expression tree for SymPy is much more intensive. And so we have some benchmark problems that take a lot of time to do, and that's something that we want to solve coming up. I don't have a solution yet. Yeah.
Let's thank our speaker once again.